All right, good morning, everyone. Thank you for joining us today for the 7th iteration of our Text Talks webinar series. If you've missed our previous webinars, you can find the recordings for those on our YouTube channel. Before we get rolling, just a few housekeeping items to highlight. At the right-hand side of your screen, you'll see a Q&A window. If you have a question you'd like to ask our speaker, please make sure to submit it there. You can also use this window to contact our behind-the-scenes team if you're experiencing technical difficulties or if you have a more general question. Lastly, a recording of this webinar will also be available later this afternoon on our YouTube channel. Without further ado, we'll introduce our moderator for today, Dr. Eric Rowe. He is the Assistant Dean for Continuing Education at the Cockrell School of Engineering at UT Austin and also Executive Director for Texas Engineering Executive Education. Take it away, Dr. Rowe.
All right. Thank you, Javier, and welcome to our webinar. In these Text Talks, we look to share exciting and industry-relevant topics happening here at the Cockrell School of Engineering. If this is the first time you're joining a Text Talk, the format's the following. I'll introduce our speaker. He'll present for about 30 to 40 minutes. As Javier mentioned, as you think of questions, please type them in the Q&A window on the right of your screen. And at the end of the Text Talk, we'll have time to discuss your questions. Our speaker today, Dr. Ezekoye, is a professional engineer, a professor in the Walker Department of Mechanical Engineering, and program director of our online Masters in Mechanical Engineering program at the University of Texas at Austin. He is a well-regarded expert in combustion and heat transfer, publishing over 200 papers on the subject. Dr. Ezekoye's UT Fire Research Group works on emerging issues in fire safety. UT-FRG researchers work on a wide range of problems that include battery fire safety, fire forensics, wildfires, community fire risk, and loss assessments, and firefighter safety. This year, he was named one of Alcalde's, the magazine of the Texas X's, Texas 10, where they flip the script and give alumni a chance to nominate professors who have made a difference in the lives of Longhorns. Fortunately for me, I've had a chance to see that firsthand as we've worked together to build, launch, and run the online Masters in Mechanical Engineering program starting back in 2015. During this Text Talk, Dr. Ezekoye will focus on his research group's work on lithium-ion battery safety. He will discuss failure modes for lithium-ion batteries, experimental data sets, and the use of testing and characterizing battery fire failure, modeling approaches for leveraging limited availability battery failure testing data to perform consequence analysis. DK, thank you very much for sharing your work in today's Text Talk. Handing off to you.
All right, I'm assuming you can hear me. Thank you very much. Great. So thanks for the audience for participating in this webinar, in this Text Talk. And so much of what my introduction in terms of who we are is going to be addressed, but let's go into this. Okay, so the first issue is just to acknowledge the various participants and people who've really helped put what we're working on together. And so most recently, our battery work has been funded by FEMA through U.S. Department of Homeland Security, and also through the National Institute of Justice on the forensic side. So we've been working on battery forensics issues. Our research group and some research group alums are shown in orange there. And so hopefully, as we're going through this, I'll point out the different contributors and what they've been doing. In our DHS FEMA work, which was really focusing on firefighter safety in lithium-ion battery system fires in energy storage systems, we had a group of participants, and my partners in this, Ron Butler, Casey Grant, Victoria Hutchison, Judith Jeevarajan, and Amanda Kimball, were quite important in terms of moving that project along. And then we have other partnerships in terms of both software that's been provided for our use through Converge CFD and a partnership with Altec. All right, so moving forward, Eric already talked a little bit about who we are and what we do, but I'll just briefly talk about that. Then we'll just talk about motivating this area, lithium-ion battery system fire safety. I'll talk about cell characteristics and the failures, and what it means once a cell has failed in terms of the cascading failure that we actually study. So we're less in the cell issues and more on the consequences of cell failure. And so sort of we just sort of string that along to larger scale consequences, and I'll have a brief summary. And so who we are, and Eric mentioned this, and so we work on emerging issues in fire safety, and we've already sort of pointed out some of these issues. Obviously, wildland fires are an extremely important issue right now, and so we have some work going on in that in terms of installation, ignition, and ignition associated with fire brands. In this talk, we're really going to talk about battery fires, and which connect to some of our work in fire forensics. And so we'd like to understand the future of fire forensics and how to use data and models to improve the ability to understand how a fire occurred. And these obviously all connect to firefighter safety. And so, let's just keep moving in terms of this. So in terms of motivation and background, as you can see, I am not a battery person, but battery issues are obviously very important as one of these emerging fire safety issues. And so I've, been trying to learn as much as I can about battery issues, and you'll see what I'm learning, and I'll tell you a little bit about it as we go through. So it's no surprise that we're entering an increasingly electrified world. And these are good things. This is a positive. And so distributed energy generation resources are allowing a lot of different things in terms of protection of the environment and access to multitudes in the world that we really haven't started to actually look at in terms of energy resources. Immediately, the things that we see are consumer electronics, electric vehicles, and every so often, as we walk around maybe our neighborhoods, we see solar panels and obviously the connections between all of these. So the first thing I want to say is that in general, this is my opinion, battery systems are quite safe, very safe. That said, opportunities obviously exist to improve the safety and performance. And so quite a bit of work is going into performance. The University of Texas at Austin, my department, Walker Department of Mechanical Engineering, is a leader in the development of lithium-ion battery technology and other battery technology. So a lot is going on in this space, and our view is that as this is being developed, there's a real need to understand and improve the safety issues. These are old, relatively older demand forecasts. We're in 2020. So, but the growth that is forecasted for lithium-ion batteries is spectacular. These systems are going to continue to be used. I was disappointed that we didn't hear about a million-mile battery, but there still are lots of opportunities and lots of development in this space. And again, what the applications are. We see this routinely. Perhaps less so is sort of an awareness of what happens at grid scale. So we see this in our phones, which are on the order of, say, 10 watt-hour systems. And so this is a varied audience. So I'm going to be speaking to some people who are experts on the battery side, some people who are experts on the fire side, others who are just interested. And so I'm going to offend everybody, basically. Laptops, you might imagine, maybe are 50 to 100 watt-hour systems. And so we're talking about sort of the energy available or the capacity of these systems. You might have 100 kilowatt hours within an EV, but you could have 1 to 2 megawatts in a containerized, just one of these little containers within a larger energy storage system for grid scale or utility scale applications. So there are lots of scales in terms of what we're dealing with here in terms of the focus. Now, one of the important aspects of renewable energy and sort of sustainability is the circular economy. And many of you know this, and this is shown on the left here, that it would be great if we could recycle and return things to some sort of previous state after use. And that's wonderful. That's something that I think that societally we want to move towards. So we view that as an important issue, but there's another circular economy that's associated with safety, and that's what you're seeing on the right there. And so as cells are being used in various types of applications, there's a logistics process that's occurring too in terms of storage and transportation, use, end use, transportation throughout, and there are these stop signs and checkpoints that standards and in our terminology, sort of working with fire service and codes and standards officials, authorities having jurisdiction to evaluate the overall safety of these types of systems. And so this is borrowed from a friend and colleague, Ron Butler, mentioned earlier. And so based on sort of his holistic view of safety in these systems, this is something that we think that is an important aspect of this other circular economy. It's a safety circular economy that we need to be thinking about. Okay, so I'm not trying to, again, sort of be the bearer of bad news and all sorts of doom and gloom, but bad things happen in uses of batteries. And so we want to understand those cases so that we can design systems to mitigate any types of failure. And again, failure data is relatively hard to get for battery systems. We think it's 1 in 10 million cells, but it's very difficult to assess the frequency of failure. But every so often, cells do fail. So on the left, you see somebody is running a little, gig economy business by charging scooters in their garage. Well, in Fairfield, California, and so you see this in the top right, somebody was doing something very similar with electric bicycles and charging them and having this little business out of their garage. Unfortunately, there was a fire there. And again, at this point, I can't say if the fire was because of the batteries, but there was a fire, and fires happen. So fires happen routinely. The fact that there were batteries there increased the consequences. And so from that perspective, it was elevated to a hazardous materials fire. Several firefighters and police officers, so first responders, were hospitalized because of some of the toxicity issues associated with the fire. And they actually had a shelter-in-place order go for that neighborhood and surrounding neighborhood. So you see that the street has been closed off, and there's lots of news stories about this this hazardous materials problem. So we need to understand what sensor systems, what detection systems, what suppression systems, for example, might mitigate something like that. Similarly, on the bottom left, we see perhaps an EV in a garage with an energy storage unit. Well, immediately to the right there is an accident that happened in Montreal in 2019, where a Hyundai Kona was in the garage, and you see this gaping hole in the garage roof, and you see the door of the garage blown across the street. So there was a failure. The failure was centered around the Kona's electric vehicle systems, and so this explosion, as much as it damaged the property, it could have been even more. It could have graver consequences had people been injured in this. And so again, how do we address that? How do we deal with it? In terms of, again, transportation, I'm going to start at the top right. So in Houston, there was a train car carrying recycled batteries, and the conductor noticed that there was some smoke coming out of the one of the cars and stopped, and subsequently there was an explosion, and so you see the deformation of the car, and windows were broken up to about a mile away. Fortunately, it was a relatively sparsely populated part of Houston. But again, if, for example, first responders had responded to the initial notification that there was some smoldering or some sort of fire within a rail car, they could have been severely injured because of that. I think it's sort of interesting because on the left there, in Bakersfield, California, a semi-trailer truck was carrying lithium-ion batteries, and again, smoking. Then the driver noticed that there was something wrong with it, and the driver stopped. Fortunately, because of awareness of the potential hazmat and explosion possibilities, first responders just shut down the highway and were much more careful in terms of the response than may typically occur. And so, so again, that's part of the transportation and recycling story. In Queensland, Australia, and this is actually happening, in the US, it's happening, I'd say all over the world really, is that improper disposal of batteries is causing fires both in transport, and that's all sorts of different places, and also at recyclers. We've gotten smarter at the University of Texas, for example, in terms of what it means to deposit batteries, used batteries, because of the fear of fires in trash receptacles. In terms of commercial and academic facilities, there was, again, renewable energy is providing all sorts of opportunities for the storage and use of electrical energy. And so, not surprisingly, some of these big box retailers and places where they have warehousing, Amazon and Walmart, were putting in solar panels and energy storage, but it's really the solar panels. So solar panels and energy storage oftentimes go together. But in the case of these solar panels, there were some fires there, and there were issues associated with the connections, and so fires happen, but fires happening potentially with battery systems and first responders and other people who may be close to the scene would pose a problem. And so one instance of this is shown in Griffith University here. I don't know, I guess I didn't get the link right on this. So Griffith University in, I believe in Queensland, in Melbourne, I believe, it was in Brisbane. There was a fire in a battery room on the 5th floor of a green building, and this first responders arrived, and the first responder was fortunately not severely injured, but was injured in a blast that occurred in that battery room. So again, these are things to be aware of. We've mostly focused on utility type conditions and utility scale because of the larger number of batteries that may occur there. And to the right is a energy storage system containers that had a failure, and this is outside of Brussels. And again, first responders, responding, trying to figure out what's happening. Fortunately, nothing dangerous happened. Again, in this particular scenario, occupants of the nearby towns and villages complained about respiratory issues after this accident. In some sense, at a much, the costs are modest or moderate in terms of the damages. There were several fires that occurred in energy storage systems in South Korea in 2018, 2019. And that number continued to increase. I mean, it was initially 25, 26, it just continued to climb. And so, again, there were environmental issues, sort of use issues in terms of why these fires and failures occurred. And again, it's something that we'd like to understand better so that we can minimize these types of losses. Closer to home is a failure that occurred in Arizona. It's a town called Surprise, Arizona, not too far from Phoenix. And it's a, so you see the top right here, containerized 2 megawatt hour ESS with 64 amp hour cells in modules that are stacked in a rack. So you see the bottom right here, this is from the DNVGL report, this rack 15 where the failure occurred. What I think is interesting is when you look at the racks adjacent to it, how relatively little damage there is to those compared to this initiating rack. So a single cell failure cascaded into a module failure, into a rack failure that drew responses from first responders, because that's what they do to make sure that that this system is safe for the owners. And in the process of responding to it, and after waiting hours for the threat to diminish, they were trying to make it safe, understanding, again, that this was a relatively hazardous condition, and several firefighters were severely injured in the explosion that occurred afterwards. And you see that doors were blown off the hinges. A firefighter was blown through under this chain link fence about 75 feet away to where that burning debris is shown there on the top right. Okay, so why do we care? Well, I first discussed the fact that there's growth in this market, and there's demand for energy storage, there's demand for lithium-ion batteries. But after accidents like Surprise, and after sort of a general awareness that maybe we aren't considering all the safety implications and issues associated with these systems, people are responding negatively. There's you know, it's damping down the demand, even though there may be other positive reasons to move forward with these types of technologies. The inability, or at least perceived inability, to make them safe enough, and that's a question, that's a moving target oftentimes, has caused, again, some concern. And so these are the types of issues that we want to address through research. And you might ask yourself, you say, well, why do these failures keep happening? What's going on? And this isn't unique to batteries or battery systems. This is true of immature technologies. We're transitioning our energy system in a way that there's just very little data available on what to expect and what might happen. So this is a sort of well-known diagram that's adapted from some work done in Japan, Shiraishi and Furuta, who talk about the fact that as you look at the percentage of failures that occur with technologies, in the early times, early stages, everything is essentially unknown. And so it's these unknown conditions and phenomena that are triggering failures. And research is one of the bridges that helps us understand better how to think about those technologies so that improvements can be made, so that some of this understanding can be codified. And given that it's codified, then fewer of these failures are associated with unknown issues. It's known issues. So as we learn more, we know, well, yes, we should have designed against that because we know X, Y, Z. Eventually, these things become human error, and obviously the failure rates in general presumably will go down. So these are the types of issues that we're wrestling with this relatively immature technology. And the other thing I want to just emphasize is that we're talking about systems, really. So it's not really just the cell or the battery, it's the battery system, and lots of different components to that. This is a test that was conducted by the FAA in a fire-resistant container. So let me walk you through what the issues are. So there are 18650 cylindrical cells in this fire-resistant container. A fire's deliberately set in there to understand the ability of a suppression system to extinguish the fire. The suppression system extinguished the fire, but the cells continue to go into thermal runaway. There's this cascading failure that I'll talk about some more. So as the cascading failure occurs, there's a buildup of flammable gases that leads to an explosion. Well, that's not that different actually from what happened in Surprise. This is much earlier than what happened in Surprise. So we're starting to see that we can actually connect the dots in different incidents under different conditions to show how failures occur in battery systems in these bad sort of bad consequence or bad direction events. So that's a sort of a placeholder to think about as we move forward. So one of the big issues it's true in all of engineering science, and it's true in this aspect of engineering science, is that as you try to bridge scales, you have to lose some detail in terms of understanding what might happen at the larger scales. So if, for example, we're interested in the consequences of the fire in terms of consequences of the failures in terms of fires or explosions, and that might be at the far right here at the site scale. So it could be a room, it could be a building, it could be a container. This is due to some failure that occurred in the cell. And that failure in the cell could have been a manufacturing defect. It could have been a failure of the software system that's operating either the cell or the module that contains the cell. And so bridging these scales, again, is the challenge. And so we've tried to at least try to understand how failure at the smallest scale might affect things at these larger scales. And so the photos that you see here are what might be, different cells that might be used in a system. And so there's a cylindrical cell, there's a pouch cell there, and these are packaged into modules. These modules are packaged into racks. You can have these in rooms, much like server rooms, and then you can have many of these at a site. So to perhaps understand and bridge that, there has to be some systematic framework or systematic process to evolve the understanding at the cell scale to the module scale to the battery scale. But batteries are expensive, so you could be if you want to analyze a megawatt hour system, well, very few people have the $1 million to just burn, and we certainly don't. And so from that perspective, there is increased use of models as we upscale. So even looking at a rack, you might be spending, in terms of testing, $100,000 or more to really understand how a battery rack fails and what the issues are associated with that. So obviously there's the need to minimize full-scale or close to full-scale testing, yet try to engage in as much testing as you can at smaller scales to understand what might happen at these larger scales. Now, having said that, randomness and material property changes and all of these other variations affect what the final result might look like. And so we try to incorporate probabilistic estimates of parameters and statistical models to upscale some of these predictions so that it's not a single number, it's not a delta function. We're saying, okay, it is this. Well, we want to say, what is the space of results that we can imagine predicting given what we know at smaller scales? And this is well known in structural engineering and in civil engineering disciplines. So a little bit about causes of failure. Just checking my time here. So in terms of causes of cell failure, we first have to start with what is a cell made of. And a cell is made up, it's a layered structure where, and so this is for a cobalt oxide system, where there's an aluminum current collector, a cobalt oxide, or some sort of oxide cathode, a separator material, and the separator material is a thermoplastic, an anode, which is oftentimes a graphite type anode or carbon anode with some sort of a binder, and the binder might be like PVDF is one of the binders, and it's a thermoplastic fluorinated system. And then there's this copper current collector. And so all the happening is going on these relatively thin scales, but that are superposed or added together to form what is the cell itself. And we'll see that shortly. And this is all filled with an electrolyte so that it can shuttle the ions across. So one of the issues is, well, what does failure mean? And so the failure that we're interested in is a thermal runaway event. And this is something that we have known for a long time in fire science and in combustion science. And that's just the fact that you may have conditions where the exothermicity, which is the rate of reaction shown by this orange line, is an exponential dependence on temperature. So as we increase temperature, the rate of heat generation increases. Well, the losses that we typically see in these systems, and certainly in the early stages, are linear in the temperature. So we imagine there are conditions in which the losses are more than, at any given condition, are more than the heat generated, and so we're in a stable operating condition. Once the heat generation is above the losses, then we are in a thermal runaway condition. Now, depending on what the environmental temperature is, we could always be in a situation where things are going to run away. And so this is the comparison of this orange line to this dashed line, where the heat generated is always larger than the heat dissipated. And so in that case, the temperature is going to continue to increase, and we're in a thermal runaway regime. And it's various reactions that occur within the cell that allow these to occur. And unfortunately, all the material is built into the cell to allow this thermal runaway event to occur. It depends on really the temperature that occurs within the cell. And so adverse operating conditions can lead to these thermal runaway events. Okay, now, these can be triggered because of manufacturing defects, for example. So contamination effects. So the requirements in terms of battery assembly require that we don't have metal shavings or filings that are potentially deposited in this layering process as we're creating the electrodes. And so these are all important issues that one has to consider. Welding defects may occur, and again, this might lead to some sort of internal short in the system. And so separator tears, if we have a tear in the separator, then it's more, we can have an internal short within the system, and that again causes problems. We'll talk about a case in point, the Samsung Note 7, where unfortunately for Samsung, there were two battery failures that occurred in, one in sort of the primary and then in a recall. And in these situations, it was a defect in the design, probably for battery A, that the pouch was crimped, and so the electrodes were bent, and so these negative electrodes being bent meant that there were opportunities for plating and internal shorts that occur within the cell. In the battery B, it was a different problem. It was a short that was dealt with. Because of some burrs, really, of improper manufacturing on the positive electrodes that pierced the separator and caused this short to occur. So manufacturing issues are critical in terms of minimizing cell failures. Electrical abuse is something that can and should be dealt with because of the battery management system. And so if you have an incompatibility, so this sort of speaks to the idea that this is potentially a system failure, because if you have an incompatibility between your charger and your battery and it's not designed appropriately, you may have conditions where you're overcharging or you're over discharging or you're putting too much current into it. And so one of the movements right now is for, say, lithium metal anodes, because of the capacity that you get with a lithium metal anode. Well, one of the challenges with that is that dendrites form, and so early battery work, my understanding is not a battery person, was to really look at these lithium metal anodes. But the fact that you were getting dendrites, and these dendrites, so the dendrites are just are growths that are coming off of the surface in sort of a fractal type geometry. And so these were piercing the separator and causing a short because, again, the separator is allowing the lithium ions to pass through, but not allowing the system to short. So from that perspective, once you provide a short circuit and poking a hole through the separator, you have failures. And so in a plating situation, if your lithium ions are unable to insert themselves within your active material on your anode side, you get a plating process that occurs, and you get this dendritic growth off of it. So these tubular structures are these dendrites growing off the active material on the anode side. So this is, hopefully will run, and this is an 800 milliamp amp hour pouch that we filled in our lab using just a simple overcharge process. And so what we were doing is we were actually studying the effect of the packaging. And so the packaging here we're looking at different types of packages, whether flame retardant or non-flame retardant packaging, and the impact that may have on the overall burning process. But in the overcharge scenario, it's relatively easy to fail an overcharge, as you just saw. What you're doing is you're dumping much more energy into the cell than it's designed to accommodate. Mechanical abuse sort of it's pretty clear in terms of what it refers to. And so as you think about a mechanical abuse condition, this could be a bending, it could be some sort of vibration, it could be impact. And so as you look at this BYD electric taxi in China, there was an accident. Again, there's deformation of the battery. Deformation of the battery causes an internal failure that, again, looks like one of the things you could see in a manufacturing defect, which causes an internal short, heating, thermal runaway, and bad consequences. Thermal abuse is what we do in our lab, so I'll speak more about this as we go through. But you see sort of different configurations where we thermally fail cells, and so we'll thermally fail a given cell and allow that propagation to occur. I'll talk a little bit about battery protection systems. And battery protection systems are great. So battery cells have protections built into them, but if you have a significant enough failure event, it's incapable of dealing with this severe environmental condition. So some of the cell level failure detection protection systems, and I put detection in there because detection is an important aspect in both cell, module, and site protection. Detection is critical, and so we'll talk more about that. But positive temperature coefficient. So cells can be built with something that will limit current under high temperature conditions, and so the PTC is something that does that, and it's a graphite and polyethylene mix or carbon polyethylene mix that increases resistance as it gets hot. Shutdown separators are also important in terms of minimizing thermal runaway events because, again, of overheating. So current interrupt devices, same kind of issue. People are adding flame retardant chemistries or have evaluated flame retardant chemistries in the electrolyte, and there's been some positives associated with that. Solid state electrolytes are a direction people are looking in terms of minimizing these cell level failures. From a sensor perspective, some sort of failure sensor is important, and this is work that was actually done here at UT. So Mike Haberman and I were looking at, so Tyler McGee was the person who actually did this work, looking at ultrasonic recognition of an overcharge event. And so the question becomes, if you can make this ultrasonic testing low profile enough, maybe that's an indicator. And obviously improved manufacturing is also very important. Okay, now, as I said, there are hazard conditions that you simply cannot protect against because of the fire started somewhere else and you're trying to minimize the consequences. And so the sequence of events that causes exothermicity are very complex, and really there is no consensus on the rates and the paths that these take. So as a combustion person in gas phase chemistry, we have a pretty good sense of what causes a flame to occur, or what the process of ignition looks like. Well, this becomes harder and harder as you go to condensed phase systems. So understanding ignition in a condensed phase system is much more challenging, or what sort of the kinetics of degradation and pyrolysis in condensed phase systems. And so this is, I think, an order of magnitude more challenging because it's an engineered system, and not unlike polyurethane pyrolysis, but the exothermicity that you get internally, and the fact that there's oxygen generation even within the cell, and that's a critical point. So in the cell, in the anode reactions, and so the anode reactions could be things like the solid electrolyte interface, and so there's a passivation layer on the anode active material, and this can decompose, it can regenerate, and there are reactions and exothermicity associated with that. And there's also generation of hydrocarbons associated with that. So we have some of the lithiated carbon reacting with the electrolyte. We have hydrogen generation. So we're generating hydrogen, we're generating hydrocarbons on the anode side. At later stages, as it's getting warmer, we're getting cathode reactions at high states of charge that are releasing oxygen. So we have a hot system with oxygen generation on the cathode side and hydrocarbon and hydrogen generation on the anode side. Well, you get gas phase reactions even within the cell, and bad things happen. So, so those are sort of like the issues that cause this problem to be challenging. Okay, so moving on to some results. We and others have been making measurements of the composition of gases released in a thermal runaway event within a cell. And so one of the things that, is a concern is, well, it releases flammable gases like hydrogen on the order of 20 to 30%. Well, that's troubling, right? It's releasing carbon monoxide, a toxic gas, on the order of 20 to 30%. Well, that's not good. Total hydrocarbons on the order of 10%, and CO2 as sort of the byproduct of some of these other reactions that are occurring inside. So it's a flammable mixture. And our go-to system for evaluating this is called LibVega. I'm just checking the time. Oh boy. And so this is our system for evaluating this, and we fail cells and cell arrays within this, and then do gas analysis. And so Robert Kennedy has worked quite hard on producing this, and he recently gave an SFPE webinar that went in depth into some of the results that he's shown. So we've done this as a function of the state of charge for single cells and arrays of cells. And one of the interesting issues here is the fact that while single cell failure is sort of the predominant way of characterizing these systems, in a thermal runaway event where it's cascading, the array might be more useful in terms of understanding it, and it's somewhat different. As we look at the composition data, then we ask the question, well, what does this composition mean in terms of laminar flame speeds as an example? Because the laminar flame speed is going to be directly as a direct input into the explosion hazard, because the turbulent flame speed is going to be based on the laminar flame speed. And we see that there are differences in chemistries associated with, not surprisingly, associated with the composition of the vented gases. The rate of release is extremely important. So if we're trying to design a ventilation system, or just in terms of understanding what the heat release rate for failed modules or failed racks might be, we have to understand the rate of generation of the gases. And so Robert has done a nice job in understanding how that might scale with the state of charge. Haoxian Yan is looking at, well, what, given these gases that are evolving, what does it mean from an ignition hazard perspective, and how might we be able to understand better if a cell caused an ignition and a fire as compared to if it was the victim of a fire? And so he's built up several systems to understand what the gas production looks like in terms of temperatures and heat fluxes, and what the ignition hazard looks like. And so sequence of events, you see that this is a single 18650 cell, and the gas production and luminosity associated with it, temperatures in an inert environment. So he'll run this for inert, so for a nitrogen co-flow and also for an air co-flow. And temperatures are, nearly 1,000 degrees Celsius for the inert environment. So you know that these things are coming out incredibly hot. In the air environment, it continues to burn. And so we sort of see the temperatures within the system continue to increase. But then you also look at the heat fluxes. So we measure the heat fluxes, and you can have up to 0.4 megawatt per meter squared heat flux for the air environment compared to about 0.1 for megawatt per meter squared for the inerted system. Why does this matter? Well, this matters again for ignition processes. So the top is an ignition event for 100% state of charge, complete destruction of this polyurethane foam, 75% state of charge. You see it's sort of delayed, and there's some consumption, but and quite a bit of consumption, but not as much. 50% state of charge and 30% state of charge. All of a sudden, we're not seeing all that much damage. So if I'm an investigator and I know, and now the question is, how do I know? And I know that the battery that was burnt up was at 50% state of charge or 30% state of charge, I'm less likely to believe that it might have been the battery that caused the failure. And again, these are the types of things that we're trying to understand, and there's a lot more work that needs to be done there. So solid ignition in general is a complex process that requires heating, obviously mixing in of the vapors to flammable condition pilots, and in fire science, we have a process called a flux time product that allows us to understand how things are ignited. So these can come together with some of the work that we've done to understand that better. And I'm going to wrap up soon, but I just want to talk about multiple cells and sites. So Robert Kennedy and Eric Archibald have looked at propagation in these types of systems. And so we have an array of pouch cells. I think these are 10 amp hour cells here, and 10 of these. And so prior to failure, post failure, because of a thermal event, and you got a propagation. And Robert has been able to sort of characterize the impact of that in terms of pressure and temperature within the environment, within the space. But this understanding of this rate and modeling of this rate, which Serhat Bilyaz and Robert have been working on, allows to come up with global kinetics to understand what cell propagation looks like, and then using uncertainty propagation, understanding how the parameters influence it, we can then issue predictions for consequences associated with this. Same ideas can be done for, this is an experiment that was done by Lopez, Mukherjee, and Jivarajan on 18650s, but we can now understand also the effect of details like the geometry on temperatures and thermal runaway. Sort of pushing it down the line, what does this mean in terms of much more detailed modeling? And that's work that we're doing. So at the module and rack level, there are protection systems again, and they're going to be detection systems, but there are a whole host of protection systems that occur at this. And one of them is insulation. And so we're looking at the effective insulation. So if this is sort of, these peaks represent cell-to-cell propagation events. And there's a time associated with a cell failing and the next cell, the adjacent cell failing. With 1 millimeter of insulation, I think, again, these are these 10 amp hour cells, this is significantly increased in terms of the time it takes for failure to occur. Perhaps with cooling, with phase change materials, we're able to extend that. All right. Very last thing, promise, is we have an experimental system for large-scale testing where it's densely instrumented in terms of thermocouple data, heat flux data, flow meter characterization, burners that we can dial in information with, and heat flux gauges and thermocouples, as I said earlier. Most recently, gas sensors have been added to it. We do then these failure studies of, say, laptops within it to understand if a laptop were to fail and we have heat flux detectors adjacent to it, what is the heat flux and what ignition events may occur because of that. We do larger capacity cell testing there to understand, given this is a 94 amp hour cell that's put into a module, that's put into a rack, what does this failure event look like? You can look at our YouTube channel, utfireresearch.com videos to see some of these. Really quickly, here's a single cell failing within this module system. And that was a single cell that failed. There are 14 more cells that are failing. This is the geometry here is about 16 feet across, 8-foot ceiling, 20-foot depth. So we can measure the heat fluxes from that and temperatures. Eric Archibald then has done looked at the experimental temperatures in this at high elevations, low elevations, the heat fluxes, and then modeled this using an open source CFD tool, Fire Dynamic Simulator. And one of the things he found that was really interesting is that the housing matters a lot. So the polycarbonate housing has a really important impact on predicting these temperatures and heat fluxes accurately. Same things happen for racks, and in this sequence, for racks, here are temperature measurements. Temperature measurements on cell propagation on those cells as this thing fails. And we don't have time to, I'd like to leave some time for questions. So room scale, we're doing simulations at room scales, room scale fire protection. And when I say the protection systems, I'm not meaning that these things necessarily work. It's very hard to get sprinkler sprays into a rack. Mist, I'm not sure that that's been looked at in enough detail, but clean agents have been looked at, and I think they have a place in terms of the fire protection. But in terms of managing thermal runaway, I think it's pretty clear, both between the FAA, Surprise Arizona, that the cooling isn't there to cause thermal runaway and cascading failure to occur. Sensor systems are critical in terms of whatever you do with this. I haven't talked about explosions. Fires, yes, explosions also. So this is a mannequin that we put in front of a closet that was built to simulate what might happen in a residential configuration if there's energy storage within a closet. And this is a simple single 94 amp hour cell that we thermally fail and that causes an explosion. This is just a little GIF of it. So that was the cell. Not a whole lot there. Site level explosion prevention. So one of the obvious ways to do this is deflagration vents. And so Austin, Baird, and others in our group have looked at what does it mean in terms of coding the tool to predict what kind of deflagration vent you need. We're filling in some of the gaps of, are these really the right models to use? Ventilation systems are important in terms of keeping the environment below a flammable limit, and there are also other systems in place. So to close, I don't want to give the impression that batteries are dangerous. Battery systems are generally quite safe, and this is our future. So I think we have to embrace electrification and the use of batteries as the storage mechanism for them. Failures do occur, and as others are improving the performance of battery systems and cells, we think it's extremely important for us to focus on the safety systems, and we're using experiments and models together to improve the safety of these types of systems. There are amazing challenges and lots of good work to be done in terms of upscaling small scale results to larger scale consequences. I hope I left time for at least one question.
Whew, that was a great topic, TK. Looking at all the questions in the Q&A window, we may need to put a short course or workshop together.
Great idea.
And you know, even just looking around my office, I think I have 6 devices just in my room here. So let me go ahead and lead with one question at least, and then hopefully we'll get room for another. And you touched on this, but are we doing ourselves a disservice when we speak about lithium-ion battery safety by discussing all battery chemistries in the same light? Shouldn't industry standards research treat the fire mitigation requirements for NMC and LFP very differently, given the difference in their thermal runaway and off-gassing?
Yeah, no, that's absolutely, that's an excellent point and question. And so, energy density is important. I mean, so LFP is I would arguably say a safer chemistry. I saw some results recently. So Matt Pace at PNNL just put out some work with some other folks, and I apologize to those other people that I don't remember their names exactly, where I was shocked to see there was 50% hydrogen, 50% concentration of hydrogen released from an LFP cell. Now, the temperatures that they reached were much lower than NMC, for example, so for the nickel-based cathodes, but still, I mean, if there is another fire event, so forget about the failures within the cells themselves, but if there is a fire or some other thermal event and I'm releasing 50% hydrogen, that bothers me. So I do agree that, yes, you know, there are very important differences that we have to look at between different battery chemistries, and we certainly can't lump them all together. But energy density and performance are huge drivers. And so to first order, if I want performance, I may be in quotes, sacrificing or trying to have to figure out a different way of handling the safety issues associated with it. So this is something that we are very happy to explore, partner, discuss, work with, and we're actually proposing and doing some LFP testing coming up.
And then I'm going to ask one more quick one, then we'll hand over to Canavis to wrap up. So we talked a lot about small electronic systems. So lithium-ion batteries are pretty ubiquitous in small electronics. There's still some cost prohibitive nature to large home installations and backup. What's your view of that future application? And then, and you may want to skirt this one, but what's your opinion on the Tesla battery home backup solution?
I want one. So no, I think this is the future. I absolutely embrace this. I think that there are clearly opportunities for improvements. I think that this idea of, you know, $50-ish per kilowatt hour, right? I mean, is just that's incredible. That's insane, right? And so I think that, yeah, I mean, I think that there are, it's something that we should be aspiring to. I think that it's, you know, let's move forward with these technologies, but let's just understand that just like the failures are system failures, the solutions are going to be system solutions also. And so I wouldn't sort of pick on any given aspect of it. I think we have to develop this both, you know, this ecosystem in terms of code standards, auxiliary sort of devices that allow us to protect against any failures that might occur in these systems.
Well, thank you so much, Dr. Ezekoye. We really appreciate your time and taking the time to present to the public around this interesting topic. And, you know, that is the future. And so we have to prepare for it. So thank you to all who joined us today. We really appreciate your outstanding questions. We want to formally thank each of you for joining, and I hope the conversation was valuable. Next, we wanted to highlight a few of our our professional development short courses and future webinars. As you heard from our speaker, lifelong learning and research is fundamental in preparing individuals to remain competitive in today's workforce. To support the needs of working mechanical and petroleum engineers, UT Engineering has created an online mechanical graduate certificate in controls and a petroleum engineering graduate certificate in data analytics. Both of these graduate level certificates are created for degree seeking and non-degree seeking students to provide you the tools to optimize processes and systems that you use every day. So perhaps you haven't been in school for a while, but interested in learning more. So please visit our website and to learn more about our simple application process. Good leadership is always needed in tackling some of the world's biggest challenges, such as battery fires. And so we at Texas Engineering Executive Education have carefully created a certificate program that pinpoints tools and methodologies to tackling leadership challenges for STEM professionals. The last class in our series is still available for registration, so visit our website to learn more. Next, we wanted to quickly highlight the upcoming energy-related courses with pipeline technology and measurements classes. If you or your organization need additional training in this area, please contact our PTEX department today. We also want to thank the 3 units of the Cockrell School of Engineering that had a fundamental part in putting this program together. First is the Texas Engineering Executive Education, who works to reskill and upskill companies' current workforce, either through our master's degree programs, graduate certificates, or short courses. So if you have a need around STEM education or training, make sure to contact our department to learn more. Next is PTEX, the Petroleum Extension of Texas. This department has been around for over 75 years, serving the oil and gas professionals either through e-learning, publications, online and in-person training, and we have the training to meet your oil and gas needs. And last but not least is our research relations team. This team partners with industry to solve some of the world's biggest challenges in energy, water, transportation, wireless communication, and many more. The Office of Research Relations works to facilitate and derive high value from research collaborations between companies and UT's researchers. Please email the Research Relations Office to initiate discovery discussion. All 3 units are here to serve you either through education, training, and research. So feel free to contact us at any time, and we would love to collaborate on helping you reach your company's full potential. As we continue in our Text Talk series, I wanted to make sure you're aware of our upcoming webinar. On October 8th, Dr. Filippo Magallani will be discussing the engineering material surfaces for extreme environments. This webinar will address the challenges understanding materials that are needed to keep machines operating in extreme environments. With the need for businesses to continue to operate despite all the changes in nature, I know this is going to be a great discussion. We hope each of you join us for the future webinar, so mark your calendars today. If you would like to provide feedback on today's webinar or suggestions for future topics that may interest you, please include them in our survey following this presentation. Once again, we'd like to thank you for joining us today. We hope you have a great weekend and hook 'em horns.